if we can see that. So we will use the definition of the orthogonal to apply or to extend to our definition here. And from this one, if we have a plane, okay, if you have a plane here, okay, and I said the plane is the W, okay, and my question is, if we have a vector V here, I mean the vector W in this plane, so what is the vector that that orthogonal with W? Okay, so the answer is the vector like this, right? Okay, and we call W1 or W prime here, but uh but the question is, this is only vector that perpendicular to this vector, to the vector W. The answer is not. Why? Because we can because we can extend W prime here. I mean that you can stretch W prime, right? Okay. You can start the W prime here. And we obtain W prime prime. Okay. Or you can you can if you multiply with some scalar, with the minus, with a scalar that is the negative, so we can obtain the vector W prime prime or W triple prime here, right? And you can see that the direction is the same. Okay, and you can see that the three vectors W prime, W double prime, and W triple prime are the same, right? So what does it mean? It means that uh, maybe it's not have only one vector that perpendicular with the vector W here. Okay, so that's lead to our definition, right? Oh, okay, that's lead to our definition. So this definition is the definition for the orthogonal complement of W. Okay, what does it mean? It means if we have W is the subspace of the real inner product space V, then the set of the vectors in V that orthogonal to every vector in W is called the orthogonal complement of W, and we denote by the symbol W perp. Okay, this one we call W perp. Okay, so from our definition, we can write that the set the W perp is the set of the vector Y. Okay, the set of vector Y. Ensure that Y is the element in V. Okay, if the element in the big space, it means the vector space V, and this vector has the property that Y dot the inner product of Y and X is equal to 0 for all X, for vector X in the subspace W. Okay, this one is a definition of the W perp. If we write the definition of the W perp as the set here. Okay, so when we have a new definition, so the first question in linear algebra, we need to make sure that this set is a subspace of V. Okay, so the first question is the set W is the set W perp a subspace of V. Okay, and for the second one, so from the definition you can see that if we have W, we will have the W perp, right? And our question is, what is the intersection of W and W perp? Why we need to show that? Because if we can show that what is the intersection of W and W perp. So we can make sure that W and W perp are not have element in, are not have the element, are not have the common element except the zero vector. Okay, so this is our equation number 1 and number 2. And okay, what did it what I answer for 2 questions? So the question is true. Okay, what does it mean? It means that if we have W is the subspace of the real number space V, and then number 1, the W perp is the subspace of V, and for number 2, W intersect with W perp is the set of the zero. Okay. Okay. So to prove number 1 and number 2 is quite easy. It's not hard. So for number 1, how to prove that this set is a subspace of V? So you need to prove that if we let the two element in W perp and scalar, and we let any scalar, then we need to show that the addition of two vectors, the addition of two vectors of W perp is also in W perp, and the scalar multiplication with the element in W perp is also in W perp. Okay, so this is how to prove that W perp is a subspace of V. Okay, so this one is very easy. Okay, and we note that W perp from definition we know that W perp is a subset of V. Okay, then so that's why we let the vector x and y in W perp and k be any scalar, and from this one we know that this one is the x inner product of x and W is equal to inner product of y and W, and equal to 0. Okay, for every W, for every vector W in subspace W. Okay, then what does it mean? Okay, so if we find the inner product of U plus V, okay, so from this one we use the axiom of the inner product to distribute as two terms here, and this one is equal, and this one is equal to 0, and the second term is equal to 0, right? 0 plus 0 is equal to 0. Okay, and next we calculate the inner product of the kx and W, and we use the axiom the axiom of inner product to pull a k out. Okay, and this one is the k multiplied by 0 is equal to 0, and this one is true for all vector W in subspace capital W, right? What does it mean? It means that x plus y and kx are elements in W perp. Okay, so this is how to prove W perp is the subspace of V. Okay, it's not hard. Okay, so for the number two, we need to prove that the two sets W intersect with the W perp and the set of the zero vector are equal. Okay, so that's why we prove that W intersect with W perp is a subset of the set of the zero vector, and prove that the set of the zero vector is the subset of W intersect with W perp. Okay, so for the first one, so we let x in the W intersect with W perp. Then from the definition of the intersect for the definition of the intersection of the set, it means that x is the element in W and in W perp, right? What does it mean? What does it mean? X is in W perp. What does it mean? It means that if we use x if we find the inverse of x with any vector in W, that the inverse of of x and that vector is equal to 0, right? But we know that x is the element of W. What does it mean? It means that from definition of W perp, we have the inner product of x, okay? So the inner product of x and x is equal to 0, right? Okay, so I will highlight. So the x from the first one is x from the x from W, and for the second one is the x from W perp. Okay, and from the definition of the element in W perp, it means x inner product with any vector in W is equal to 0, and because x is the element in W, so that's why the inner product of x and x is equal to 0. And from this one, what does it mean? So this implies that the vector x is equal to 0. Why? Why is implied that x is equal to 0 vector? Yeah, because of the positive axiom of the inner product. Okay. So this is how to prove the first. I mean how to prove that this leg whole. Okay, and for the second leg, we need to prove that the set of 0 vector is the subset of W intersect of a W perp. So this one is quite easy. Why? Because we know that W and W perp are subspace of V. What does it mean? What does it mean is a subspace? It means that the 0 vector, the set of 0 vector, is the subset of W and W perp, right? And from this one, we can conclude that the set of the 0 vector is the subset of W intersect with W perp. Okay, it's quite easy. Okay, if you need to copy this page, so please pass it. Okay, and from this one, we know that if we have so for the definition of W perp, so we know that if we have W, we can find the W perp, right? And from this one, we already know that W perp is a subspace of V, right? So this leads to our question: if we need to find the orthogonal complement of W perp, what does it mean? It means that what is the orthogonal complement of W perp? It means that W perp and perp. Okay, so what is the orthogonal complement of W perp equal? So I think the question, I think the answer is quite easy. Okay, so the answer is, I think it's maybe equal to W. Okay, I think everyone I think everyone will know will think about this. The complement, orthogonal complement of W perp is equal to W. Okay, but this one, so the question is it true for any subspace W? Okay, is it true for any subspace W? So this question I think is quite hard. I mean, I think actually it's quite hard to find it, but we will have we can show that this one is true, but it's true for a special case. Okay, what is a special case? So if we know that W is the subspace of the real finite dimensional inner product space V. Then we can show that the orthogonal complement of W perp is W. So that is W per perp is equal to W. Okay, what does it mean? It means that if we have the vector space V and V is the finite dimensional, okay, what is finite dimensional vector space? Yeah, it means that we have the finite element. We have the finite element of the basis, right? I mean, the basis has a finite element, okay, and if we have a finite if we have a finite a finite of the finite of basis element, so W is the subspace of V, of is also has a finite a finite basis element, right? Okay, so, and the proof for this one is quite hard. I mean, it's I mean we require we require many steps to prove this theorem. But if you need to read the proof, so I will give a proof to you. Okay, so the proof is like we have 2 pages for proof. Okay, so this one actually this one is a set. Okay, so we need to prove that W per perp is the subset of W, and W is the subset of W per perp. Okay, for this for the subset that for the case that W is the subset of W per perp, it's very easy. Okay, why? Because if we let W if we let any vector W in the set of W, then we know that W the inner product of W and X is equal to 0 for every W, right? For every W perp. Okay, why we have this? Why we have this? Because because we know that if we have W, so we also have a W perp. Sure. So that's why we can show that W is in the element of W per perp. Okay. So for and for the in the case that the W per perp is a subset of W. So I will give you a sketch proof. Okay, first we need to show that V, a vector space V is the sum of the two vector, if the sum of W and W perp. What does it mean, the sum of W and W perp? It means that every element in V can be written as the sum of the sum of vector in W and W perp. Okay, and for the proof, I think it's very tedious. Okay, so if you need to read the proof, so please pause it. Okay, and we quite use many we quite use many proof or many topics to show this. Okay, and next if we can show that V is the vector space V is the sum of the W and plus the W perp. Okay, and next we will show that if we let the basis B1 is the basis for W and B2 is the basis for W perp, so we need to show that B1 union with B2 is linearly independent. So the proof is not hard. Okay, so you can read this. Okay, if you need to copy this page, so please pause it. Okay. Okay, next we move to the next slide. Why we will prove that the basis of W union with the basis of W perf is linearly independent, because we will use because we will use the dimension. Okay, we will use the dimension here, and we can show that uh and we can show that from V, if because we know that V is equal to W plus W perp, and then V is the span of the vector of b1 and b2, right? And what is the vector of b1 and b2 here? So b1 is u1 to uk, and b1 is v1 to vl, right? And we can count, and we can find the dimension of w. I mean, we can find the dimension of v, right? What is the dimension of v? The dimension of v is the number of the element in uh, in the basis, right? And this one we have a k plus l. And what is k? K is the dimension of w, right? Because w has because we assume that w the number of elements in the basis for w is k, and the number of the element in the basis for w perp is l. So that's why we obtain this equation. Okay, we obtain that the dimension of v is equal to dimension of w plus w perp, and this one is true for every subspace v. For every subspace w of v. Okay, and if we can show that, if we can show this equation, so this one is quite easy. Why? Because we know that w perf is a subspace of the v, then dimension of w perp plus the dimension of the w perp is equal to dimension of v, right? And so we obtain this equation. The dimension of w perp plus dimension of w is equal to dimension of v, and dimension of v is equal to dimension of w perp plus dimension of w perp, and we can cut the dimension of the w perp on both sides, and we obtain that the dimension of w perp is equal to dimension of w. And then since w is the subset of w perp, and the dimension of w perp and the dimension of w is equal, what does it mean? It means that w and w perp are equal. Okay. So the proof is quite, I mean, it has some technique, or some technique of the linear algebra. Okay, and we use the dimensional. Okay, we use dimension to prove that w perp is equal to w. So if you need to copy this page, so please pull it. Okay, next we will move to the example. I mean, this example is not hard for you. Okay. Okay, if we let w is the subspace of the R6 that's spanned by the vectors w1, w2, w3, and w4 like this. Okay, the question is to find the basis for orthogonal complement of w. Okay, so how to find this one? Okay, from this one, you can see that what is w? W is the spanning, I mean the span of w1 to w4, right? This one is the set w, and we already know that this set is the subspace. Okay, is the subspace of R6. And the question is, we need to find a basis for w perp. Okay, so how to find the basis for w perp? So the first one, we need to find what is the set, or what is the w perp. Okay, or what is the set of w, of the orthogonal complement of w. Okay, and how to find it? Okay, from this one, we already know that W is the subspace of R6. Then from this one, we can conclude that W perf is a subspace of R6. What does it mean? It means that you can find, you can find the element of the W perf, right? One thing that you know is W perf is the element in R6, like this. Okay, so we denote it as the x. Okay, so the perf is the set of x, x1, x2, x3, x4, x5, and x6. Okay, and this set is a property that the inner product of x and w is equal to 0 for any vector w in w, right? So this one is the set of w perf. Okay, so if we can find the relationship between x1, x2, x3, x4, x5, and x6, so we can find so we can show so we can find that what is the element in W perf. Okay, so this is our solution here. Okay, because we know that W is the subspace of R6, then W perf is subspace of R6. It means that W perf is the set of the the six tuple, okay, six tuple here, x1, x2, x3, x4, and x5, x2, x6, okay, and this vector, if we use inner product, okay, with the vector x and any element, any vector in W, so the inner product is equal to 0. Okay, and from this one, I think from this one, you can see that if we need to find the element, if you need to find to find x1 to the x6, so you need to substitute W, right? So you need to substitute vector in W to obtain the equation. But you can see that W is the span of the W1, W2, W3, and W4. So it suffices to from this one, it suffices to show that if we use W as W1, W2, W3, and W4, is enough. Okay, so that's why we obtain 4 equations here. So we use x, the product of x and W1 equal to 0, and this one is equal to x, the inner product of this one. So okay, so if that, if the problem that did not give you the inner product, so you can use the standard inner product for that vector space. Okay, so for the R6, the standard inner product for R6 is the Euclidean inner product. Okay, so from the x inner product with W1 is equal to x1 plus 3x2 minus 2x3 plus 0x4 plus 2x5 plus 0x6 is equal to 0. And next, from x, the inner product of x and W2 is equal to 0. So this one is equal to, we obtain this equation, 2x1 plus 6x2 minus 5x3 minus 2x4 and plus 4x5 minus 3x6 equal to 0. And the third one, we obtain the equation 0x1 plus 0x2 plus 5x3 plus 10x4 plus 0x5 and plus 15x6 equal to 0. And for the x inner product with W4 equal to 0, we obtain the equation 2x1 plus 6x2, 0x3, 8x4, and 4x5 plus 18x6 equal to 0. And we need to solve this equation. Okay, so how to solve this equation? Yeah, we will use the matrix. Okay, we will use the augmented matrix to obtain the reduced low echelon form, right? to find the relationship between the x1 to the x6. Okay, from this matrix. I mean, from this equation. I mean, we have a system of linear equation. We obtain the matrix like this. Okay, and if we use the elementary, if you use the elementary row operation, you can show that the reduced low echelon form of this matrix is equal to this matrix. Okay, and this one we can see that the first column, the third column, and the sixth column is a pivot column. Okay, so uh, so the x1, x3, and x6 are basic variables, and x2, x4, and x5 are free variables. Okay, so that's why we let we declare a free variable. Okay, so we let x2 is s, x4 is t, and x5 is r, where s, r, t are real number, be any real number, and then from this, and then we can show that x1 is equal to minus x2 minus x4 minus 4x4 and minus 2x5, and we substitute x2, x4, and x5 here, and from x3 we have x3 is equal to minus 2x4, and we substitute x4 by t, and x6 is equal to 0. So we can find that the W perp is the set of the x1, x2, x3, x4, x5, and x6, right? It's the two, and it's a 6 tuple, and now we already know the relationship between x1, x2, x3, x4, x5, and x6. Okay, so x1 is equal to this is equal to the minus 3s minus t minus 4t and minus 2r, and x2 is s, and xt is the minus 2t, x4 is t, x5 is r, and x6 is 0. Okay, where the srt are any scalar or any real numbers. Okay, and from this one we can write this form as the term of s, t, and r. Okay, the first term is the s multiplied with the minus 3, 1, 0, 0, 0, 0, and the second term is a t multiplied with the minus 4, 0, minus 2, 1, 0, 0, and the third term is the r multiplied by minus 2, 0, 0, 0, 1, 0. And what does it mean? What is this set equal to? So this set is equal to the span of two vectors here, right? Okay, and now we need to find that what is the basis for the W perp. Okay, it's easy to see that this set is linearly independent, right? Why this one is why this set is linearly independent? Because if we let the first and the second vector, okay, so two vector, I mean the first two vector are not scalar multiple, right? And the third vector is not we cannot write the third vector in the linear combination of the first two vector. Okay, that's why this set is linearly independent. So so the basis for W perp is this set. Okay. Okay. So this is the solution. Okay. Okay, if you need to copy this page, so please pause it. Okay. From this one. Okay, before we end we end of this video. We end this video. So we have some remark about this example. So you can see that from this one, you can see that the first row of this vector is W1, right? This one is W1, and The second row is the W2, and the third row is W3, and the last row is W4, right? Okay. And now we can we use this one to obtain to obtain the row echelon form like this. Okay. Okay. So this one is look like it look like you find you find a basis for the row space, right? If you can remember about the row space of any matrix. Okay, so from this one we can show that. Okay, we can show that actually this one so the span of W1, W2, W3, and W4. So this one is, what does it mean? It means W, actually, if we have a matrix like this, so the span of W1, W2, W3, and W4 is the row space, right? If we denote this matrix is A, so W is the row space of A. Okay, and what is this one? So this one is like you find the you find the answer, right? You find the answer of the AX equal to 0, right? And what is this? What is X? So X is the answer of the AX equal to 0. So from this one we will obtain we will find what, find the null space of A, right? And from this example, it means that we can show that if we find the row space A perp, so the row space of the perp of the row space A perp is equal to the null space of A. Okay, and from this identity we can show that the null space of the A perp, the null space of A perp is equal to row space of A. Okay, this is so this is we can obtain from this solution, from this example. But if you need to prove this, I think the proof is not, it's not hard. You can prove it by yourself. Okay, so I will give you to the homework. Okay, show that the row space of A perp is equal to null A, the null space of A, and the null space of A perp is equal to row space of A. Okay, that's the end of this video.